Okay, good day, students. Welcome to the first section of Chapter 6, which is called Sequences as Discrete Functions. It starts on page 354 of your textbook. Previous video you may have already watched went through this Blackline Master 6.1 called Chapter 6 Prerequisite Skills, and I just walked through each question looking at some solutions just to get you started. If you haven't already watched that, this video is going to assume that you have the necessary skills, so we're just going to get started. What I want to do to get you excited about this chapter is just to introduce the very first chapter problem, which you'll find in your textbook on page 362. It's number 12, and it's called the Koch snowflake. And I'm just going to go to this website, and so here we are at shador.org. And what I wanted to show you is just a little bit about a background. So this individual in the early 1900s was playing around with patterns, and it starts off with a very, very simple straight line, and the pattern, which is called the generator, takes the initiator, and they use special terms called iteration 0, which is the very first step, and then iteration 1 is actually the second step after having followed this generator pattern. And what you're doing here, as you can read on the screen, is that you're taking the original line segment and you're replacing it with 4 new segments. Each are 1/3 the length of the original, and this is repeated on all line segments. And you get a sense of how this develops. This portion here in the middle of the screen you can see there is called the Koch curve. And when this is started on a equilateral triangle, I'm going to just cycle through some of the stages of this. You get a very interesting shape developing, and this is called the Koch snowflake. And after 2 iterations, it's quite complex, and if you go any further than that, it really does look like a snowflake, and this would be quite difficult to draw. So I'll just point out that when you're doing this activity, chapter problem number 12, you probably won't be able to go much past this second iteration, and that's going to be the extent of it. And in each case, what you're tracking are the lengths of the line segments, the number of line segments, and the perimeter of the snowflake, which is going to help you to explore this idea of an explicit formula. So this is one of the definitions we'll get to in our lesson today. So I'm going to go back into the notebook file. Here we are. You're going to have something which is called GeoPaper, and you need to have this or something which allows you to start this investigate on page 354. You could just use graph paper, I suppose, as well. And what you're going to do, if you follow the steps here, is you're going to start out with a 16 by 16 unit square. You're going to locate midpoints, you're going to connect them, and you're going to continue this process, making smaller and smaller squares inside the original until you can't work with it any longer. And as you go in this activity, you're going to be recording the number of regions. So what I've done is I've gone to liberty of drawing this out, nice colorful picture here, just to show you what this is going to look like. And each time, of course, you're counting the regions. I think maybe if you like technology, this is a really good time to use the Geometry Sketchpad file, or program rather. And what you want to do in this case is start off with, if you choose to use this approach, start off with going into graph, and you're going to set the grid form, and I would suggest you go to a square grid, and it should look something like this to start with. You can control the size of the grid. You'll notice, of course, that I've already overlaid on top of that some points, and these points you want to go right on the intersections of unit values. So the way to do that is to select snap points, and when you select snap points, it's going to lock these in, so you can only place it at certain locations. So you want to start with the 16 by 16. In case you're wondering how this square was produced, it's just a simple matter of choosing your line tool on the side menu bar here, and with snap points you're just going to be drawing from your corner locations. And once you have your straight lines, then what we want to do is take advantage of the software here, and we're going to apply this iteration, which is this repeated process of selecting midpoints. And the way to do this is first to select the sides, and you'll notice as soon as you do that, they have this blue highlight over top of them, and that tells you that that side has been selected. And with all 4 selected, you're going to want to go up here to construct midpoints, which you'll also notice is a quick key, which is Control M. And I've already actually done that, and you'll notice that as soon as I apply Control M, midpoints are now also highlighted, and from the menu you can go and construct segments, but I'm going to use Control L, which is going to immediately create all 4 segments between those highlighted midpoints. The nice thing, of course, at this point is I could stop, I could count the number of regions, and I would have, in that case, 5 regions, middle square and the outside triangles. And I'm going to repeat my process. I'm going to apply another iteration. I'm going to select midpoints, Control M, and I'm going to Control L again, and that's going to construct that next square. So now I can count my regions, and I would be looking at that interior square has now been divided into 5 segments. So I'm going to be adding 4 more to the previous total. So I'm going to be continuing to update my table, counting the number of squares and the number of regions. And if I want, I can just back up this process and I can say when I have 1 square, I have 1 region. And if I repeat this, when I have 2 squares, I have 5 regions. When I have 3 squares, I have 9 regions. To tabulate this, I would be looking at my file and I would be filling in these values. So if we go back to the smartboard here, just write these in here. So we said 1 square, 1 region, 2 squares was 5, and 3 was 9. I'm just going to add one more iteration to this process, and when I add that 4th square, again, I'm going to divide that interior square into 5 pieces. There was already 1 region before, so I'm really just adding 4 more regions, and that's the pattern. We want to recognize that for each additional square, we're going to be adding 4 more regions, so I can easily fill in this entire chart if I wish to do so, and I could go all the way down to the bottom, just adding 4 at a time, and then the next step in the investigation is to graph this. So when I've got all these points, I have more than enough to graph to get a sense of what this sequence, this pattern of numbers looks like. Okay, so I'm going to take my number of region values, which are called terms, and I'm going to plot these on a grid paper. Now keep in mind we've got 4 quadrants here, but I'm just going to be interested in plotting positive term numbers. And the term numbers are the number of squares. And notice we started at 1. So the y-intercept for this graph isn't really going to be meaningful, because actually if we were to back up the pattern by 1, we would be looking at 0 squares having -3 regions, and that doesn't really make any sense. So we don't want to plot the n equals 0, and that's appropriate because when we're plotting sequences, the very first term is n equals 1 always, and that's called the term number. The variable n is used. So that's an easy way to track it. You'll also notice that the term value itself is denoted with the letter T, and that's quite common as well. And when we return to my graph then, I'm just going to be looking at plotting just a couple points to get the sense of what this looks like. You may have already figured out, well, it's going to be linear, of course, because the rate of change is 4. I'm going to actually move away from this grid. If you have graph paper right now, you can plot these points. I would recommend at least a half a dozen just to get the confidence that in fact it is following a linear pattern. We're not trying to at this point find the equation, although that comes next in the investigate. I'm actually going to show with Geometry Sketchpad a really quick way to do this. Again, I already had the window up of the iteration process for midpoints of squares. If you want to create a new sketch, just go to File, New Sketch. I already have one made. So I'm going to go back here, and At this point, you'll see your grid. That has been placed there by defining a coordinate system under the graph menu. Under grid form, I would just leave it at the default. It should be a square grid. All right, you notice I've relocated my origin to the bottom left-hand corner. That's just because, again, quadrant 1 is our quadrant of interest. I'm going to choose the dot tool here, and I'm just going to plot a couple of points. 1, 1. We have 2, 5, 3, 9, 4, 13. That gets me enough data points just to be able to draw a line through them. I'm going to choose from the line tool array. That's just going to make it really easy to start at one point, and I'm going to go through the others there, and there's my line. And at this point, it's positive slope, quite steep. Rate of change is 4. We can see the step pattern over 1 up 4. I'm just going to talk a little bit about the use of the line in this example. Now we've plotted this and we've connected our points, and that's a pretty natural thing to do. But we might just pause and think about, is it appropriate to connect the dot? Well, to answer this question, we have to consider the independent and dependent variables, and I just want to label the graph a little bit here so you can follow along with my explanation. Thinking about the number of squares, which we're using the variable letter n for, and the number of regions, I think we decided was going to be t for term value. And in this case, we look at the domain and the range, I think, to answer this question, because we have distinct points, and it's obvious that those are not in dispute here. But what is in between the points? So is there any data between n equals 1 and n equals 2, or n equals 2 and n equals 4? And of course, the answer there is no. The number of squares, which is our independent variable, has to be whole values, and of course this is the term number, and these are natural numbers. Natural numbers are 1, 2, 3. So those are whole values. There's no data between them, so really to plot a line between the points, it just doesn't hold up. And really that's the best explanation. We're trying to determine if a function is discrete or what's called continuous. Discrete doesn't mean secretive, but rather it just means that the values are whole values, and typically the domain and the range are countable values, things that are whole. The contrast with something that is continuous, on the other hand, would be the functions that you're familiar with, that you've plotted in the past. Continuous functions such as y equals negative 3x plus 6, or y equals 3x squared subtract 6. Linear or nonlinear, these are functions where in the past typically we have just said x belongs to the set of real numbers, and we know that we can put in lots of different numbers for our input value, whether they be whole values, whether they be natural numbers, or they take on decimals, positives and negatives. And of course here we're definitely limited with only positive term values starting at 1. And I'm going to get you to think about how you'd find the equation of a line at this point. Okay, I'm back now, and I've just put up a solution here which will just save us a little bit of time when we show videos. You won't have to be waiting for me to write. You can look at the steps I've gone through. We're finding the equation of a line which has form y equals mx plus b. I mentioned previously that the y-intercept was negative 3, so we're just working this out algebraically. It doesn't have actual significance or meaning for the equation, and what we're trying to find here actually is the explicit formula, but you would just call it the equation of a line. And working from the slope, which is 4, that was a known rate of change. 4 additional regions were added every time we put a new square into the interior. We use 1, 1 as a known point. Any point on the line will work, and from that we're solving for the y-intercept and writing the equation. And I'm just restating that this is the explicit formula, and I'm doing a couple things here. I'm just introducing, first of all, that this is a function. This is a discrete function relating number of regions t sub n to the number of squares n. In this particular case, I could use function notation f of n, or I can also use the t sub n notation, which you will want to become more familiar with, so I want to work from that at this point forward. But you also observe here an additional condition that needs to be placed on this function, and this is really the domain. n is the independent variable, so the domain would be the values that it can take on, and they have to be natural numbers. And again, natural numbers are those that start at 1 and they increase from there up. These are really just the positive integers. I'm just giving an example of how this explicit formula works. It's very similar to function notation. You substitute the input value n, and your output value would be your function value. In this case, term 4, we place 4 in for n. 16 subtract 3 gives us 13. So the fourth term is 13, and we knew that from before. The sequence was 1, 5, 9, 13. There's our fourth term. Below that, we could represent the term number, and again here it had the first term, the second term, the third term, the fourth term. At this point, I think we've established enough of the basics for this section that I'm just going to summarize and wrap up. I'd ask at this stage that you would go through the examples in the textbook, beginning with the first example on page 356, and just skimming your way through to the example 4 on page 359, 360. And the key concepts on that page, I'm just going to summarize in a quick note, which you can copy as is, or you can generate your own note based on your writing styles. Okay, back again. Here's the handout, which is part of this lesson. Sequences as discrete functions. I've just put a central title for the graphic organizer here as number pattern functions. These are functions that are based on sequences of numbers that have a certain pattern. In this example, with the number of regions and squares, we looked at a particular type of function called an arithmetic function, or an arithmetic sequence, where addition was what linked the numbers. And going down to the summary of these key terms, most of them have come out in my lesson, just starting from the word sequence, ordered lists of numbers with natural number domain. The function values, the range, are called terms. We looked at a discrete function, and a discrete function is basically what we would use to model a sequence. Its graph has separate points that are not connected. Continuous functions, on the other hand, we don't use for a sequence because they often have real number, domain, and range values which can take on more than just whole values, and their graphs can be connected with points. Typically, when I plot f of x equals x squared, that's what I would call a continuous function. X can be more than just 1, 2, 3, 4. It can take on negatives, it can take on fractional values, and there's no limit to what we can put in for x. And of course, we do connect a graph of f at x equals x squared as a smooth curve between points. Continuing on, clockwise here we have the word term, which is found by substituting the term number into the explicit formula. Explicit formula is shown over here, where this example illustrates 4 term values and their corresponding term numbers below. And finally, of course, the term number. The key thing in remembering is that this is the label, or the order of the term. It starts at 1 and may stop or go on indefinitely. So here's your note for the section. You want to come in tomorrow having looked at some of those examples as I mentioned and studied them, be familiar with the terms, and this would be the assigned work we'll have a look at tomorrow. Okay, take care.